Hey class, in this recording we're going to talk about blood clot removal, blood clot disorders, and blood clot management. As we look at our blood clots, these clots are going to have retraction occurring within 30 minutes of the initial clotting formation of those thrombocytes or platelets. The platelet-derived growth factor is going to be secreted by platelets themselves that are coagulating or clotting, I should say clotting together, not coagulating, clotting together. And the endothelial cells, the cells that line the blood vessels. We also find that this platelet-derived growth factor serves as a mitotic stimulant. So when platelets clot together, they stimulate a chemical that causes the endothelial cells to start to reproduce, and that's going to cause there to be fibroblast activity and smooth muscle activity as well to help repair the damaged blood vessel. So a blood clot is going to release chemicals that speed up the healing and recovery process of the blood vessel. The process of removing a blood clot is known as fibrinolysis. The blood clot is held together, or the coagulated blood, that platelet plug, is going to be held together by a fibrin mesh. And if we lyse or break apart the fibrin, we're going to dissolve the blood clot. There won't be anything to hold it together anymore. That is fibrinolysis. Factor 12 speeds up the formation of an enzyme known as kallikrein enzyme. And I know it doesn't say kraken, but every time I look at this word, I think to myself, release the kraken, even though it says kallikrein, not kraken. And this kallikrein enzyme is going to take plasminogen and turn this plasminogen into an activated plasmin. So we'll have plasminogen free floating in our blood plasma. It's just kind of hanging out there. It's just ready to act. It's like, can I do it now? Can I do it now? It's just ready to go. And once it's activated, it goes from plasminogen to being plasmin. And once it's in the plasmin form, it's had a small conformational shift, and now it's an enzyme that is going to actively and rapidly break apart fibrin monomers to dissolve the fibrin mesh. So, let's diagram it with a flow chart here. We have our factor 12. Factor 12 is going to help us to make kallikrein. Kallikrein is going to take plasminogen and turn it into plasmin. And then plasmin will take the fibrin polymer and break it down into a fibrin monomer. And this whole process is another positive feedback loop. So we have a positive feedback loop to initiate coagulation and clotting, and then we have another positive feedback loop to break apart the blood clot itself. And this particular positive feedback loop ends when there's no more blood clot. There's a nice end point here for this particular feedback loop. Although positive feedback loops in general just scare me. Now, as we're looking at this process, we don't want inappropriate clotting. Inappropriate clotting is a big deal. If once clotting starts, it is a positive feedback loop. So we need to have mechanisms in play to make sure that clotting doesn't start unless we really want it to. So we have that protocyclin coated line, that the blood cells have the endothelium that's coated with protocyclin. That's one way. We keep the platelets from sticking to the side of the blood vessels. We also have thrombin dilution. The thrombin itself is diluted by rapidly flowing blood. So as we look at this process, as long as the blood is continually moving, or we have high rates of movement, that thrombin is going to be less likely to initiate coagulation. It's when the blood is moving slowly that we're at risk of spontaneous clotting, particularly with the intrinsic cascade. And this is, I think of like my siblings, because this has happened to a couple of my siblings. They were flying in an airplane, sitting coach. They had a 10-hour flight. They were curled up in a ball to save money by sitting in coach, because all of my siblings are like 6'2", 6'3". And they had those deep vein thrombosi in their lower legs, in their calves form, because the blood was moving very slowly through the veins in their lower legs. We also are going to have some natural anticoagulants in our bodies. We can have heparin that can be released from basophils or basophils that are differentiated into mast cells. Heparin is going to interfere with the prothrombin activator, and if we can't have a prothrombin activator, we're going to have a really hard time of making our thrombin. We also have a chemical or a protein known as antithrombin that will deactivate thrombin before it can get to the fibrinogen. So we have some mechanisms that help to down-regulate this feedback loop. Thank goodness. But we still have clotting disorders. Any kind of mutation or deficiency or in excess, too much vitamin K, too much calcium, for instance, can cause the coagulation cascade to be overactive or underactive. Common one, and this typically is going to be, and if you take a genetics class, you'll see this example, and then a Russian family tree of the Russian czars, the Russian royal family. We'll talk about hemophilia, and this is a hereditary disease, a group of hereditary diseases that is going to be defined by a deficiency of one of the clotting factors, or some other multiple clotting factors. Some of them are going to be sex-linked, and that they are going to carry the recessive mutation on the X chromosome. So generally speaking, these will manifest in males that only have one X chromosome. Hemophilia A and hemophilia B are the two examples. Hemophilia A is when someone doesn't have factor 8. Hemophilia B is when they don't have factor 9. Hemophilia C is when somebody is going to be missing factor 11, an autosomal-based hemophilia. Now, as we're looking at these blood clots, hemophilia A is a problem because we really depend on the factor associated with hemophilia A. And if we have too much physical exertion, we get very tiny blood tears in our blood capillaries that can just bleed and bleed and bleed, and that leads to lots of pain, excruciating pain, as blood pools and causes pressure for the individual. So how do we treat people with hemophilia A? They need constant blood plasma transfusions or injections of purified clotting factors. They typically will get their factor 8 being produced by transgenic bacteria or bacteria that have been genetically modified with human genes to make factor 8 for human beings. In particular, individuals that have hemophilia A will get a lot of hematomas. A hematoma is just a mass of clotted blood in the tissue of our bodies. So if we think of a subdural hematoma, that's a very common one that my wife deals with in her medical practice. Somebody gets bonked in the head, and then in the subdural space of their brain, blood will pool between the dura mater and the arachnoid mater and just pool and build up. We can have this blood pool and clot in multiple spots. If you had to choose between a subdural hematoma and an epidural hematoma, I personally would choose the epidural hematoma because it's a lot easier to relieve the pressure. That blood clot will be directly beneath the bones of the cranium, whereas the subdural hematoma is going to involve going through that dura mater, that really tough membrane, to relieve the pressure from that blood clot. We also find that if somebody has a thrombosis, they have lots of abnormal clotting in unbroken blood vessels. A blood clot that initially forms in an unbroken vessel, so we need to emphasize unbroken clots are called a thrombus, or plural thrombi. And they typically are going to occur in the legs of inactive people, or people that are going through a period of inactivity. And then the thrombus, the blood clot, forms and it's stationary. It stays in one spot, and then that person stands up, they get up, they start moving around, and it goes from being stuck in one spot to all of a sudden it's moving around. And the moment that blood clot is moved around, it goes from being categorized as a thrombus to an emboli. So when a thrombus breaks free, it's now an embolism. And when we look at the diameter of blood vessels, these thrombi typically form in the veins of the legs. And the veins of the legs will pump blood back towards the heart. And as we're going back towards the heart, the veins get larger and larger and larger. So these thrombi almost never get lodged in a blood vessel as they're moving closer to the heart because the blood vessels keep getting bigger and bigger and bigger. It's after that thrombi travels through the heart, it's now going to exit the heart through the pulmonary arteries and start going towards the lungs, and that the blood vessels start to get smaller and smaller and smaller. And that's why whenever we hear the word embolism, most people immediately think pulmonary embolism, because that's where the overwhelming majority of the emboli get stuck, because that's the first part of our circulatory system where the blood vessels start to get smaller again to catch the emboli or the embolus. Now, as we're looking at infarction, infarction is a technical term for tissue death, but this is tissue death that has occurred from blocked blood supply or blocked blood flow. So we can have a MI, myocardial infarction, or a stroke, or as my wife lovingly refers to them, a brain attack. And when we look at these infarctions, we have hundreds of thousands of them in America every single year. Thromboemboli are a major killer of Americans. They're a big deal. So let's say you're somebody who has excessive clotting. You might need some help managing that. The goal is to prevent excessive clotting and to dissolve your existing clots. So when we look at these, how to prevent clots, first we have vitamin K. And vitamin K is needed for the formation of clotting factors. And if we can somehow neutralize that vitamin K, we can make it, typically through competitive inhibition, we're going to make it so that we're less likely to initiate the clotting cascade. So we have coumarin, warfarin. These are two vitamin K antagonists. And here's some fun trivia for you. Warfarin is a blood thinner given to people that have too much blood clotting, or if you put it in a tray and cover it with peanut butter, you call it rat poison. Warfarin and rat poison are chemically the exact same thing. Vitamin K from leafy green, we typically get vitamin K. We have vitamin K1 and vitamin K2, two different variations of vitamin K. We get a lot of vitamin K from the E. coli in our large intestine, or from eating dark green leaves. Leafy, think spinach or kale, has lots of vitamin K in it. Something else we can do to prevent clotting is take aspirin. Aspirin is going to suppress thromboxane A sub 2, which is one of the factors of the clotting cascades. And then we have other anticoagulants that have been discovered via animal research. Medicinal leeches, and I think this is just awesome. Leeches used to be part of the standard physician practice. You would have incense, you would bleed so you'd make the patient breathe in incense, you would bleed the patient to restore the balance to their four humors, and then you would cover them in leeches and maggots. That was standard medical practice hundreds of years ago. But back in 1884, it was found that leeches actually do a really good job of removing blood clots from tissues that you don't want the blood clots in. And we think of a leech, it's an organism that specializes in sucking your blood. So these organisms probably are going to need some way to open up your blood vessel and prevent the clotting cascade from preventing the flow of blood. And these leeches will release a chemical called hiruidin. And we also find that snake venom from vipers contains a chemical compound known as avarin that also prevents the coagulation cascades. So I just had to show you this picture of a medicinal leech. Look at this guy. This is enormous. This is a thing of nightmares right there. Oh my gosh. Oh, I just need to cover it up. Oh, I don't want to look at that. So when we look at these medicinal leeches that can dissolve blood clots, or clots that have already formed, they aren't the only kid on the block that can do this. There are also bacteria, streptococcus, that are going to dissolve our blood clots by releasing an enzyme called streptokinase. And the streptokinase can be injected into a human being and break up a blood clot in a coronary vessel. And this streptokinase is going to break apart blood clots while a person is having a heart attack. But there's a downside. The streptokinase digests typically just proteins. And when we think of our bodies, proteins are the single most common macromolecule. So in addition to breaking apart the fibrin that holds the blood clot together, the streptokinase is going to cause damage all over the cardiovascular system. So this is kind of a double-edged sword. It helps a little bit, but it also hurts. This is one of those situations where getting your dosage calculation is really important. We also could give somebody tissue plasminogen activator. And that's a TPA. I love the name. What does this thing do? It activates plasminogen. And if we activate plasminogen, we're going to turn it into plasmin, and then plasmin dissolves our blood clots for us. So tissue plasminogen activator is going to not digest almost all the proteins or any protein in our body. Instead, it's just going to focus on activating our natural clot dissolving mechanisms. We also could give somebody hematin. And hematin is a chemical compound. We have heme for hemoglobin in the root word. It's a chemical compound produced by the giant Amazon leech that will dissolve the blood clots while that thing fills itself up. And I remember when I was a young child, I watched a Nova documentary on PBS about these medicinal leeches. You take sausage casings and fill them up with pig blood and drop them in the aquarium, and the leeches will wiggle over to the sausage casings and just suck the blood out of them and just, oh, yuck. I hate leeches. Yeah, I had some childhood trauma. So that's all we have for this recording. If you have any questions or comments about the class content, not my psychological problems, please feel free to post them on the class discussion board or to shoot me an email. And as always, happy studies.